Unit analysis or dimensional analysis is the method that we're going to use for problem solving. And basically what we're going to do is make a unit factor, which is just a ratio from an equal relationship. The general strategy is to identify the starting point and the ending point. That's our given and find. And then identify the conversions that we'll need to get from the given to the find. And this is where those unit factors come in. So for this problem here, our given is 140 centimeters. So notice the given is a number and a unit. The find is feet. How many feet? The find is the question, and it's only a unit. It doesn't have a number yet. That's what we're trying to find. And the conversions are either given in the problem or we find them from tables. So in this case, we use the conversion tables to find that 1 inch equals 2.54 centimeters and that 1 foot is 12 inches. Now, that one is not necessarily in the table. You probably already know it, but I wouldn't expect you to know any conversions. They'll be given to you, or you'll have a table where you can find them. There's a few of the metric conversions that I want you to memorize, and they're highlighted in that table. So we identify our conversion factors, and we'll use these as ratios. So 1 inch equals 2.54 centimeters. We can write that as 1 inch over 2.54 centimeters. Or we can write 1 foot over 12 inches. Or we could do it the other way. We could say 12 inches over 1 foot. They're equal, so you can put one over the other and it still equals to 1. So you always start with your given, 140 centimeters. And then you apply your conversion factor. So our first conversion factor, we want centimeters in the denominator so that they cancel out. So the 2.54 centimeters goes in the bottom, 1 inch on the top. The centimeters cancel, and now we have inches. Well, that's still not the unit we needed. We needed feet. So now we put the inches on the bottom, 12 inches, so that those cancel, and then the 1 foot on the top. So we get, when you go to your calculator, anything in the numerator, you hit your times key. If it's in the denominator, you hit the divide. So 140 divided by 2.54 divided by 12 and gives you 4.59 feet. And then we have to consider significant figures as well. So in this case, our given number has 2 significant figures. Because it has no decimal written in it, and it ends in that 0, you kind of assume that 0 is not significant. But you know the 1 and 4 are, so we've got 2 significant figures. Our next conversion is English to metric, and that is a measurement. So let's consider that in our significant figures. The 1 is a pure whole number, so it doesn't matter. But the 2.54, that's 3 significant figures. And then the 1 foot over 12 inches, that's a definition. So those are pure whole numbers, and we also don't have to worry about significant figures. So the smallest of those is 2, and so that's why we get 4.6 feet as the answer as we consider significant figures. So now let's apply this unit analysis method to solving metric conversions. So this is one way we can solve these. And here's a problem. How many centimeters are in 0.000450 kilometers? So we start by finding our given and our find. So our given, the number and a unit, that's 0.000450 kilometers. And our find is just a unit, it's centimeters. Find centimeters. So our conversions we can find in the metric table. So I brought the metric table over here to show you a little bit about how it works. And we're not going to find a conversion from kilometers to centimeters. We're going to have to go through the base unit, which is meters. So we're going to use this one right here, kilo, and this one right here, centi. And the example is given in meters, but these apply to liters, to grams, to all of the metric units you can apply. Just replace meter with any other unit. So our first conversion is that 1 kilometer equals 10 to the third. Well, I'm just going to write 1,000 meters. And our next conversion is that 1 centimeter equals 0.01 meters. Okay? Now you may think, well, what I remember is that the 100 centimeters equals 1 meter. And that's really the same thing. So if you remember that and want to use it, that works too. So those are the conversions to get us from kilometers to centimeters. And so now we apply the unit analysis. Start with our given, 0.000450 kilometers. And then our first conversion is going to use the kilometers. Now we want the kilometers on the bottom. So I put 1 km equals 1,000 meters. Okay, that gets rid of the kilometers, and now we're at meters. We want it to go to centimeters, so we need one more conversion. So this time we want meters on the bottom, 0.01 meters equals 1 centimeter. And the meters cancel. And now we have centimeters. So now I go to my calculator. And remember, numerator hit times, denominator hit divide. So I start with 0.000450 times 1,000 divided by 0.01 equals, and that's 45. And the units are centimeters. Now if we consider significant figures, which we always want to do, let's go back to our numbers. Now, both of our conversions are definitions. They're metric to metric, so they're pure whole numbers. We don't have to worry about significant figures. So the only number that matters is our starting number, which is often true. Our given, however many significant figures are in your given number, that's how many are in your answer. So the first zeros, they are not significant, but the 4 and the 5 and the 0 are significant. So I'm going to come back and say 0.0. Because that 0 was there in the beginning, I don't want to lose it. It's a significant figure. So that's our answer, 0.450 centimeters. Now another way to do metric conversions, and you may remember this, I've learned it before, is you can just move the decimal. And so from kilometers to meters, that's 1,000, so we move it 3 places, 1, 2, 3. And then to centimeters is 2 more, 1, 2. And so that gives us the same answer of 45 centimeters. So whichever way you're more comfortable with. The moving the decimal is very easy, but it's easy to not remember how many places to move it or which direction to move it. So if you're not comfortable with it, stick with the unit analysis. That always works. So here it is written out a little bit more clearly. And let's try some more practice problems here with this method of conversion. I'll just do maybe the first one here and then leave the rest for you to just practice. And I brought the table that came from your book that converts English to metric units, because you might need that on some of these problems. So I have that in front of you so you can do it. So number 1, a recipe calls for 0.75 liters of cream. What is this in cups? All right, so remember, we're going to do a given and a find. So in this problem, our given is 0.75 liters, and the find is cups. Maybe I'll write it out, cups. All right, and so now we have to think of conversions. Well, we're going from metric to English, so let's see what our table here gives us. In our table, we have that 1 liter equals 1.057 quarts. So that we know that 1 liter equals 1.057 16.7 quarts. Okay, that gets us to quarts. And so now we got to go to cups. So you kind of have to look this one up, but 4 cups equals 1 quart. Okay, and so those are the conversions that we're going to use. We'll start with our given, 0.75 liters. Okay, and then we apply our first conversion. So we want the liters on the bottom, so 1 liter, and then the 1.057 quarts on the top. The liters cancel. Now we have quarts. And then we want to go to cups. So this time we want the 1 quart on the bottom, and then the 4 cups on the top. So the quart cancels. And now we're at cups. So I go to my calculator. 0.75 times 1.57 times 4 equals, and then I'm going to consider significant figures. The given is 2 significant figures, 2 sig figs here. This one has 4, and this is a definition. So we're going to go with 2, and I got 3.171. So I'm going to round that to 3.2 cups. All right, so that's how you approach these problems. And I recommend that you pause it here and try these others, and the next slide shows the answers. Make sure you know how to do them. Let's look at what happens if you need to raise a unit to a power. So this happens in when you want to find a volume. So there's really 2 ways to look at volume. You can have volume units like the liter, or you can use a length times a length times a length, like centimeters cubed. And that is also a volume. And so let's look at how we would do this. The conversion of 1 inch to 2.54 centimeters. So if you were going to do this problem, you'd say our given is 1255 centimeters cubed. Our find is inches cubed. Our conversion is 1 inch equals 2.540 centimeters, but that's not cubed, and we really need our conversion cubed as well. So when we look at the conversion, if you cube everything, it's still valid. So we cube the inch, we cube the centimeter, we cube the 1, we cube the 2.54 as well. And so when you cube everything, the relationship is still true. So the way you would do this problem, you start with your given, 1255 centimeters cubed, and then you apply the conversion that has the cubed in it. So remember to cube the number and the unit, and that will give you the correct answer. Another thing that's important to realize is that 1 centimeter cubed is the same as a milliliter. And so you can use these completely interchangeably. And that amount, it's also called 1 cc, is about the size of a thimble, if anybody even knows what a thimble is. But that's maybe about a sugar cube. That's what a centimeter cubed is. So here's a problem to try. Convert liters, 2.00 liters, to inches cubed. All right? So in this case, our given is 2.00 liters. Our find is inches cubed. Okay, so we're going to need that number that we just had come up with, the 16.4 centimeters cubed, equals 1 inch cubed. Okay, we start with our given, 2.00 liters. Okay, but we can't use this yet because we need, instead of liters, we need centimeters cubed. And so now we're going to fall back on this, that 1 centimeter cubed equals 1 milliliter. So first we're going to go to milliliters. And so you got to recognize back from the metric table that 1,000 milliliters equals 1 liter. Or the table would probably say 0.001 liters equals a milliliter. They're the same thing. So go with, we want the 1 liter on the bottom. 1 liter, 1,000 milliliters. And then we could just change that to centimeters cubed, but you could say 1 milliliter equals 1 centimeter cubed. And then finally apply this conversion, that 16.4 centimeters cubed equals 1 inch cubed. And now you go to the calculator and we do 2 times 1,000, and the ones we can just ignore, divided by 16.4 equals, and I get 121.9, and let's just keep our 3 significant figures, so I'm going to call it 122 inches cubed. And that's the answer. The next topic we want to discuss is density. And density is defined as mass divided by volume. And it's really important because it does not depend on how much you have. The mass depends on how much you have, the volume does. So I could ask you a question, which weighs more, gold or feathers? And that's kind of a trick question because it depends on how much you have. You might assume, oh, well, the gold will weigh more. But that's only if you had comparable quantities. And so this picture here, a brick versus a sponge. Well, the brick is going to weigh more if they're the same size, but if they're very tiny brick with a really big sponge, so with mass, it depends on the size, but density, it doesn't. So density is mass divided by volume. And dense, you know, the way you think of dense, thick, compact, heavy, that is true. You know, the brick is more dense than a sponge. And this table here gives the density of various substances. And you can see that water has a density of 1.0. And notice the units. It's grams per centimeter cubed. So it's a ratio of units, grams per centimeter cubed or grams per milliliter. Remember, those are interchangeable. So density is a quantity that we can look at, and it's unique to a substance. So aluminum has a density of 2.7. Whatever you make out of aluminum, it's always going to have that density. And you can use the density to identify a particular metal or substance. So to calculate density, we're just going to find the mass and the volume and divide them. So here's an example. A liquid sample has a mass of 4.83 grams and a volume of 2.7 milliliters. Find the density, okay? So we just find the mass and divide it by the volume. So in this case, we have 4.83 grams, there's our mass, divided by 2.7 milliliters. Mass divided by volume. Go to your calculator. 4.83 divided by 2.7 equals, and I get 1.7888. So 1.7888, continuing, but we got to consider significant figures. How many significant figures? Well, the numerator has 3 significant figures. The denominator has 2 significant figures. So we can only keep 2. We can keep the 1 and the 7. So we're going to make that 1.8. And the units are grams per milliliter. Notice significant figures and units, you always want to apply those in every problem. Sometimes the mass or the volume are measured by difference. So here's an example like that. The mass of a graduated cylinder is 79.201 grams. A liquid 10 milliliter sample is added to the graduated cylinder. The mass of the cylinder and the liquid is 87.311. So when you think about it, how do you find the mass of a liquid? Well, you can't just pour it on the balance. You have to put it in a container. So in this case, we know that density equals mass over volume, okay? But we don't know the mass directly. We have to subtract, okay? So the mass is 87.311 minus 79.201 grams, okay? The cylinder with the liquid minus the cylinder. And then we divide that by the volume, which was the 10.0 milliliters. So I go to my calculator. We've got 87.311 minus 79.201, and that's equal to 8.11 divided by 10.0, okay? And I get 0.811 grams per milliliter. Okay, and can we keep all those figures? When we subtract these two, we need another 0 here because we have 3 past the decimal, 3 past the decimal. And then so that's 4 significant figures. Our denominator has 3 and we're keeping 3, so that's good. And here's another problem. A rock of irregular shape has a mass of 21.622 grams. The volume of the rock is found by water displacement. So how would you find a volume of a rock? It doesn't follow a geometric shape. So what you can do is put it in water. So if you had a graduated cylinder with some water in it, and then you measure the volume of the water, and then you add the rock, what's going to happen is the volume's going to increase, and the amount that the volume increases is the volume of the object, okay? So this one we can measure the mass directly, but the volume is by difference. So in this case, we still have density equals mass over volume, okay? So our mass is given straight up, 21.622 grams. And then the volume, so it was 37.3 after we put the rock in, and it was 30.0 before the rock, and so that's by difference. So when we subtract those two, 37, well, that's 7.3, so we're going to have 7.3 milliliters for the denominator and only 2 significant figures. So then we do 21.622 divided by 7.3 equals, and I get 2.96, but we can't keep that many figures. We can only keep 2, so we're going to go with 3.0 grams per milliliter for that density. So here it is all written out a little bit more clean. And hopefully that all makes sense. We can also use density as a conversion factor. Sometimes you'll know either the mass or the volume, and you're trying to solve for the other, but you'll also know the density. And so the density can be used to convert between those two. Here's an example problem. A cube of aluminum has a density of 2.70. And you can always look these up. We have that table of densities, and so you can see in the table that it's 2.70 grams per milliliter. And it measures 1.21 centimeters on each side. What is the mass of the cube? So in this case, we're given the length, and we're trying to find the mass. So our given, we actually end up having to multiply the length times the length times the length to get the volume. So that's our formula for volume. So we know our volume, and our conversion factor is the density, and our find is the grams. So what we'd do here is we'd start with our given, 1.77 milliliters. Okay, so we found it in centimeters cubed, but remember that's the same as milliliters. We can use either unit. And then we're going to use our conversion factor. We want the milliliters on the bottom, 1 milliliter, 2.70 grams. On the top, the milliliters cancel, and that gives our grams. So multiply those, 1.77 times 2.70, and that gives us 4.779, but we can't keep all those. We have 3 significant figures, 3, so let's go with 4.78 grams as the answer. Okay, so that's using the density as a conversion factor. Here's another example. A gold crown has a mass of 883.39 grams. What is its volume? So here we got to know the density of gold, and so you can look that up in the table. That density of gold is 19.3 grams per milliliter. Okay, so our given is, let's see if I have these written out here. Nope. So our given is 883.39 grams. Our find is volume. Well, volume, let's go with milliliters because that's what our density has. It'd be milliliters or centimeters cubed. And our conversion is the density. So we start with our given, 883.39 grams. Now this time we want the grams on the bottom. So we'll put the 19.3 grams per 1 milliliter. The grams cancel, and this will be our milliliters. 883.39 divided by 19.3 equals, and again, significant figures, I get 45.77. I'm going to go with 45.8 because our density has 3 milliliters is the volume of the crown. And here it is all typed out a little bit more clean. Another way to find density is the triangle trick. So I like unit analysis because it's straightforward and you can always use it, but some people find this triangle really helpful. So you just take your density, so you write a triangle with a T in it, and so you put density, mass, and volume, okay? And I remember that mass over volume, so you got to have the mass on top, the volume on bottom, and the other space you put the density in. And then what you do is you just cover the one you're trying to solve for. So for example, if you want to find density, you cover that up, and it's mass divided by volume. Density equals mass divided by volume. Or if you want to find the mass, you cover it up, and you have density times volume. Or if you're trying to find the volume, you covered it up and now crossed everything out, but you will have mass over density. And so you can use the tricky triangle if you like it, if you find that easier. And so here's some humorous conversions just for fun. And this is a list of the things you really need to know from this chapter. So review those and try the practice problem.